Hello, and welcome to today's video on vectors in calculus. Let's review the objectives for today. First, we'll discuss component form of vectors. Later on, we'll discuss linear combination form of vectors. We'll discuss unit, tangent, and normal vectors. We'll also deal with differentiation and integration with vectors. And finally, applications of vectors. A vector is a quantity possessing both magnitude and direction. Here's vector u, and notice the notation, it's u with a hat over the top, so sometimes it's abbreviated u hat, and it goes from the lower left to the upper right, and it has large magnitude. Other vectors might have medium magnitude. Here vector v, written with an arrow over the top of it, is a vector pointing straight downward. And finally, here's vector w, which is smaller in magnitude and it's pointing straight to the left, and that's written in bold font. So those are the three most common ways of expressing vectors: either u with a hat over the top, or something like v with an arrow over the top, or something like w in boldface. First, vector u is expressed in component form, and it's written as 5, negative 2. What that means is the horizontal component is 5 units to the right, and the negative 2 means 2 units downward. Vector v is negative 1, 3, so it's 1 unit to the left and 3 units upward. Say we wanted to find the component form of u plus v. Well, we just add the horizontal component pieces together and the vertical pieces together. So 5 plus negative 1 gives me 4, and negative 2 plus 3 gives me positive 1. So the resulting combination of vectors u and v by addition would be a vector that would be 4 units to the right and 1 unit upward. Find the component form of 4u minus v. Well, in this case, we'll first multiply vector u by 4. So instead of 5, negative 2, it'll be 20, negative 8. And then we're going to subtract v, which is negative 1, 3. 20 minus negative 1, the horizontal components, turn into positive 21. And negative 8 minus 3, the vertical components, turn into negative 11. One of the useful techniques that we're going to need to be able to use is finding the resultant, which a lot of times is the diagonal of a parallelogram. And for that, you may want to use either law of sines or law of cosines. In this case, since I know side angle side, I'll be using law of cosines. So to find the diagonal AC, I'm going to first label AC with a variable. I chose x. Next, applying law of cosines, I would have x squared equals 4.21 squared plus 7.62 squared minus 2 times 4.21 times 7.62 times cosine of 122.69 degrees. Solving that for x, I get x to be about 10.51 centimeters. Unit tangent vectors are vectors tangent to a curve with a magnitude of 1 unit. Unit normal vectors are vectors that are normal or perpendicular to a curve with a magnitude of 1 unit. And that's where the word unit comes in. Here's a picture of a parabola, and you'll see it has 2 unit tangent vectors, one going, let's call this towards the northeast, and the other one traveling towards the southwest. The 2 normal vectors are perpendicular to the curve. One travels to the northwest, or to the upper left, and the other one travels to the southeast, or to the lower right. Say we are given the parametric equation x equals 2t squared plus 1, y equals 3t plus 5, and we're asked to find the tangent and normal unit vectors to the curve at t equals 2. First, we'll get the derivative dy over dx. In order to get that, we'll take the derivative dy dt, which would simply be 3, and we'll put it over dx dt, and the derivative of 2t squared plus 1 would be 4t. Next, we'll evaluate it at t equals 2, since that's what we were asked to do, which will result in the derivative, or the slope, being 3/8 at t equals 2. Now, the derivative, since it's the slope, it's rise over run. So that means we go up 3 and over 8. So here I drew a triangle where I went over 8 and up 3. I could have drawn the upper part of the triangle instead. I could have went up 3 first and over 8 second. And what I need to do is use Pythagorean theorem to find the hypotenuse. And that turns out to be the square root of 73. So the magnitude of this vector, starting in this lower left corner and working towards the upper right, is the square root of 73. I want the magnitude to be 1. So what I need to do is to divide my horizontal and my vertical components by the square root of 73. So what I'm in essence doing is taking a dilation of this triangle where I'm shrinking it by a factor of the square root of 73. That would make this hypotenuse 1. So if I divide each side of this triangle by the square root of 73, the hypotenuse is now 1, which makes it a unit vector. So instead of just over 8 and up 3, I'm saying for one of my unit tangent vectors, vector u, would be 8 over the square root of 73, comma 3 over the square root of 73, and vector v would be negative 8 over the square root of 73, comma negative 3 over the square root of 73, because that's the vector that starts here in the upper right and goes southwest towards the lower left. The unit normal vectors, on the other hand, are perpendicular to the tangent vectors. And when you think about perpendicular, the slopes are negative reciprocals. Well, reciprocals means I'm going to flip the x and the y, and I'm going to negate. So my vertical, 3 over the square root of 73, becomes my horizontal, negative 3 over the square root of 73. And my horizontal component in the tangent vector, 8 over the square root of 73, stays 8 over the square root of 73 because I don't want to do a double negative. Now, what I can also do is take vector u. I'm still interchanging the horizontal and the vertical components, but this time I'm leaving the 3 over the square root of 73 positive, and I'm choosing to negate the 8 over the square root of 73. So there's vector q. Incidentally, if I had worked off of vector v, I would interchange them, and let's say I negated the negative 8 over square root of 73, that would have given me the positive 8 over square root of 73, while leaving the negative 3 over square root of 73 for vector v's vertical to be vector p's horizontal. And once again over here, going from vector v to vector q, I'm interchanging the vertical and the horizontal, and this time I'm negating the negative 3 over square root of 73 to turn it into positive 3 over the square root of 73. And here's what they look like. And this is the curve for question 3. And there's one unit tangent vector, and there's the other one. There's one unit normal vector, and there's the other one. Here's an application. Suppose we have a single-engine airplane that is flying 110 miles per hour in still air in the direction 20 degrees north of east. A 15-mile-per-hour wind begins blowing in the direction 30 degrees south of west and acts on the plane. Find the resulting direction and ground speed of the plane if the pilot makes no adjustments. Well, first we'll create vectors p for the plane and w for the wind. Here I am drawing them out. Now, vector p has greater magnitude since it's 110 miles per hour, that's its magnitude, in the direction 20 degrees north of east. So I found east, and I rotated 20 degrees to the north. Vector w, the wind, is 30 degrees south of west. So I found west, and I rotated 30 degrees towards the south, and there's vector w. Now, when you think of polar form, you think, well, the x-coordinate is r cosine theta, and the y-coordinate is r sine theta. And r this time is my magnitude, 110 miles per hour if I put units on there. Cosine of my angle in standard position, 20 degrees, comma, 110 sine of 20 degrees. And that gives me the resultant for the plane is 103.366 horizontally and 37.622 north. The wind, however, since it's 30 degrees south of west, I first have to rotate 180 degrees to get to west, and then an additional 30 degrees. So that makes my angle in standard position 210 degrees. And since the wind has a magnitude of 15 miles per hour, the wind's vector is 15 cosine of 210, comma 15 sine of 210, which makes it about negative 12.990, negative 7.5. And if you think about that, that makes sense that those came out negative, because what I'm saying is it's going west and it's going south. Where the plane, both the horizontal and vertical components were positive, that means he's going east as well as north. Next, I want to add vector P and vector W together. So I just add the components, add the horizontal pieces together, add the vertical pieces together. And that gives me the resultant of what the plane will actually be doing. And in this case, instead of going 103 roughly miles per hour to the east, he'll now only be going about 90 miles per hour to the east. So he lost about 13 miles per hour to the east. And instead of going 37.6 miles per hour towards the north, he'll now only be going about 30 miles per hour to the north. So he lost about 7.5 miles per hour to the north. Here you can see the resultant drawn out. It's basically, it's almost a headwind. The wind is almost coming straight on at the plane. Now a tailwind would actually have increased the plane's vector as I go from what it would be doing in still air to its resultant. But since this is a headwind, you can see the original vector still drawn here, but now the resultant is the hypotenuse of this red triangle. You'll notice it's not as great magnitude. It doesn't go as far to the east and it doesn't go as far north because he's now fighting the wind. But I do know he's going about 90 miles per hour to the east and about 30 miles per hour to the north. And what I need to do to find the resulting ground speed is find the magnitude of the resultant vector. I'm just using the Pythagorean theorem, and I got that to be about 95.264 miles per hour. And so that's the resulting ground speed. So he's no longer doing 110 miles per hour, he's now doing just over 95. So he lost roughly overall about 15 miles per hour, but he's also being blown slightly off course, as you can see. Which brings me to the direction, where initially he was going, aiming 20 degrees north of east. Now he will be going 18.433 degrees north of east. How I found that is I named this angle here theta, and tangent is opposite over adjacent. So it's the vertical component over the horizontal component. And since tan theta equals roughly 30 over 90, I went inverse tangent of the 30 over 90 and got angle theta to be about 18.433 degrees. And then you have to put your compass directions on there. In this case, it's north of east. If it was just a little past 90, let's say the angle was, say theta was 95 degrees, then you could say 5 degrees west of north, or you could say 85 degrees north of west. Now we come to the linear combinations. We have our unit horizontal vector I, which is 1 unit to the right and no units vertically, and our unit vertical vector J, which is 0 units horizontally and 1 unit up. That makes that my vertical unit vector. We want to find vector V as we go from P to Q. If I go from P to Q, notice the horizontal piece increased 3. Notice the y-coordinate decreased 4. And so here's vector V. It's 3i plus negative 4j, or simply 3i minus 4j. Now vector U is QP. If If I start at Q and go back to P, my horizontal, I went from 5 to 2, so it decreased 3. And my vertical went from 3 to 7, so I increased 4. So vector U is negative 3i plus 4j. Here's another application. Suppose we have a particle moving such that its position vector in meters is given by r of t equals 2 sine t I plus 4 cosine t j. Again, that's written as a linear combination. For t between 0 and 6 pi, where t is measured in seconds. First, sketch the path of the particle, then find the velocity and acceleration vectors as well as the speed at t equals pi over 3 seconds. Well, here's first the graph. What I did was I put my calculator into parametric mode, and I graphed x equals 2 sine t and y equals 4 cosine t, and I graphed it over the interval stated with my calculator in radians. I could convert these to degrees and graph it in degrees if you'd like. And what I find is it's an elliptical shape, and it starts at 0, 4, and it comes over to 2, 0, down to 0, negative 4, back to negative 2, 0, ends up coming back to its starting position at 0, 4. Now it's at 0, 4 at time 0 seconds, 2 pi seconds, 4 pi seconds, and 6 pi seconds. It's at the bottom at 0, negative 4 at pi seconds, 3 pi seconds, and 5 pi seconds. And you could convert those to decimals by multiplying 3 by the value of pi, or 5 by the value of pi, for instance, if you wanted to. I also plotted the point at t equals pi over 3, since that's one of the points that we're interested in, finding the velocity and the acceleration as well as the speed at that point in time. In order to get the velocity, what I need to do is take the derivative of the position formula. So simply take the derivative of the horizontal component. 2 sine of t's derivative is 2 cosine of t. Leave the horizontal unit vector I attached to it. Then take the derivative of the vertical component. The derivative 4 cosine t is negative 4 sine t. And again, leave the vertical component vector attached to it, vector j. Next, we want to evaluate it specifically at time pi over 3 seconds. So now I'm substituting pi over 3 in for the t's, and evaluating those. 2 cosine of pi over 3 turns into 1, so I have I, and then 4 sine of pi over 3 turns into 2 square roots of 3, so I have 2 square roots of 3j, and that is measured in meters per second. And here's its picture. I actually graphed this vector coming off of this point. It's 1 unit to the right, so it went from square root of 3 to 1 plus square root of 3, which puts it at about 2.732 for the end of the vector. And then I took the y-coordinate, which used to be 2, and I lowered it 2 square roots of 3 units, so that brought me down here. And so there's, in other words, if this particle were moving along this elliptical path and somehow it just managed to just escape, like it just was let go, set free, so that it no longer followed the path, it would follow this tangent vector. Now notice I didn't put the one going in this direction because the orientation had it going in the clockwise direction. So if he was let go at this point in time or in space, he would move according to this tangent line. Now, for the acceleration vector, take the derivative of the velocity vector. So the derivative 2 cosine is negative 2 sine. The derivative of negative 4 sine is negative 4 cosine. Then plug in pi over 3 and evaluate. And my acceleration vector at time pi over 3 is negative square root of 3i minus 2j, meters per second squared. And here is the acceleration vector. And interesting to note, if you have an ellipse, which in parametric form would look something of this nature, when you do two derivatives, you'll end up back to the same trig function that you started with. However, you'll have flipped the sign. So you notice how the position formula was 2 sine of ti, and now the acceleration formula is negative 2 sine of ti. And in the original position formula, it was plus 4 cosine of tj. Now it's minus 4 cosine of tj. That makes the acceleration vector always point to the center of the ellipse. So it's always accelerating in towards the center. So if we were over here at 2, 0, the acceleration vector would move right along the x-axis from this point straight to the center. And if we were down here at 0, -4, it would point straight up, and its magnitude would be 4. So it'd be accelerating in that direction. Now, in order to find the speed, what we're going to have to do is transfer our velocity vector over to this page. So the speed at time pi over 3 seconds, and I'm just reminding you what the velocity vector is. It's 1i minus 2 square roots of 3j. If I make a triangle, 1 unit to the right and 2 square roots of 3 units down, and if you put the units on there, those are measured in meters per second, simply find the hypotenuse of this right triangle. So you have the horizontal and the vertical components. By Pythagorean theorem, you end up getting c to be the square root of 13 meters per second. That is our speed. Our speed will never be negative. So when we square root the 13, don't include the plus or minus, only go with the positive. So the speed is an absolute value. It's just simply the magnitude. It's not really giving us the direction. We know the particle is traveling square root of 13 meters per second, but like the plane problem, we'd really have to figure out the angle if we wanted to know the direction. We can see it here in this triangle, so we know we're going towards the southeast. And finally, for our last problem, suppose we were given this situation. The particle is moving such that its velocity vector is given by v of t equals the quantity 3t plus 1i plus square root of 2t plus 1j for t between 0 and 8. Find the particle's acceleration vector and position vector as a function of t, given r of t equals 9i plus 5j. We weren't given units, so we don't know if t is really measured in seconds. We don't know if the velocity is actually measured in meters per second. Could be miles per hour for all we know, so we're just going to leave units off of this problem. So to get the acceleration vector, simply take the derivative of velocity, one component at a time. The derivative 3t plus 1 for the horizontal component becomes simply straight up 3. And notice I have the I, the unit horizontal vector, attached to it. And then don't forget to do chain rule when you need to do the derivative of square root of 2t. But the plus 1 will drop off. The derivative of the square root of 2t is 1 over the square root of 2t, j. Now, as far as the position vector, we need to integrate velocity. So, if you started with position, if you took derivative, you get velocity. If you took the second derivative, you get acceleration. Working backwards, if you started with acceleration, you'd have to integrate to get velocity. And then from velocity, you'd have to integrate again to get position. And that's what I'm doing. I'm starting with velocity and I'm integrating to get position. So I'm going to integrate 3t plus 1, and then separately I'll integrate the square root of 2t plus 1. When I do, the antiderivative of 3t is 3/2 t squared. The antiderivative of 1 is t. But this needs the constant of integration, so I called that one c sub 1. When I integrate the vertical component, the antiderivative of the square root of 2t is 2 squared roots of 2 over 3 t to the 3/2. The antiderivative of 1 is t. And then it needs its own constant of integration, so I call that c sub 2. This constant, c sub 1, and this constant, c sub 2, are most likely different values. So that's why we're giving them subscripts, so that they could each equal something separate or different. Plugging in 2 for t and setting it equal to the given 9i plus 5j, I'm going to equate the horizontal piece or horizontal component, with the horizontal component over here of what was known at time 2. And I'll do the same for the vertical components. So when I clean up the horizontal component over here, I get 8 plus c sub 1. I'm setting it equal to 9. And that tells me c sub 1 should be 1. And when I clean up the vertical component, I get 14 thirds plus c sub 2, and that should equal 5. So c sub 2 equals 1/3. Your final step is to back substitute in the value for c sub 1 and the value of c sub 2. So my position vector, r of t, is equal to the quantity 3 halves t squared plus t plus 1 I, plus the quantity 2 squared, so 2 over 3, t to the 3 halves plus t plus 1/3 j. And that's all there is to it. I'm Murray Wright. Thanks for watching my video.